Okay, today's topic is quantum mechanics. Until now, we we have seen what the relativity looks like, and it resolved the problem of Michelson-Morley experiment. The direct consequence of the relativity was the existence of time dilation, and it is logically equivalent to the existence of a length contraction for a moving object. From this, the space-time coordinate transformation between any two inertial reference frame was completely rewritten to arrive that the final result for the Michelson-Morley experiment was completely explained by the Lorentz transformation. The Lorentz transformation is just like the rotation of Euclidean vector. The in the Minkowski space, the four displacement is the four vector that is covariantly transformed according to the Lorentz transformation. Out of this, we were able to construct the full velocity by taking the derivative of the four displacement with respect to a Lorentz invariant time that is called the proper time, and by multiplying the full velocity by a rest mass of the particle, we were able to find out the form momentum. And spatial component of the form momentum was understood to be the rest mass times the velocity, where the velocity is the ordinary velocity. Ordinary velocity means the displacement, uh, ordinary time derivative of the displacement. Because of the increasing mass due to the time dilation factor, that is Lorentz factor, multiplied to the rest mass, it was understood that any massive object can never sur- supersede, never be accelerated to have a velocity whose magnitude is greater than the speed of light. And then we were able to identify what the zeroth component of the four momentum is, and that was the energy divided by the speed of light. Logically, it looks consistent, but uh, it was necessary to confirm it experimentally. And first of all, the photoelectric effect was considered to find that the N4 energy, full momentum of the photon can be explained if we substitute the rest mass equals zero into the unshell relation for the full momentum. In addition, the wave frequency proportionality of the energy of the photon is combined to find that the wavelengths of the quantum mechanically treatable particle, such kind of elementary particle, follows the de Broglie wavelength. That is Planck constant divided by the momentum, where the momentum is a completely relativistic representation. Hence, we have extended our theory to the case of Compton scattering, in which, although we consider the fixed target experiment by making use of photon of the scale of X-ray or higher, we were able to approximate the system as a free particle scattering. I mean, the initial energy of the photon is much greater than the binding energy of the electron, target electron. So we were able to compute the process as a free particle scattering. And in this scattering, we try to confirm the full momentum conservation, where the zeroth component E represents the energy over speed of light, and spatial component is just the usual free momentum with the relativistic representation for the mass. And finally, in the fixed target experiment, the photon, the fixed target experiment, the initial electron is at rest and it will be kicked off. So if we compare, compare the kinetic energy of the initial and final electron, the final electron's kinetic energy is positive. Hence, the energy of the initial photon is part of the initial energy. Initial photon's energy is transferred to the scattered electron. Therefore, in the fixed target frame, the energy of the final electron must be smaller than the initial electron. If you consider de Broglie wavelength, that corresponds to the case that the wavelength of the final photon is always greater than the initial one. And because of that, there's a angular dependence of the wavelength, the shift in the scattered light. And finally, we also considered the problem in a much simpler frame of reference called center of momentum frame, in which the sum of the spatial component of the full momentum vanishes in the initial and the final state, respectively. All right, so through this, we have seen relativity is really working, and in addition, we we have seen some quantum nature of photon, and the Compton wavelength is a kind of barometer criterion in the sense that if the particle has the momentum determined by the scale of h over lambda c, that is Compton wavelength, then that is that must have a quantum nature and a relativistic nature, both of them. So intrinsically, before we go ahead with the Schrödinger theory for quantum mechanics, the birth of the quantum mechanics is accompanied by the relativity. And although we will follow the non-relativistic formulation for the time being, it is completely consistent to consider everything in a relativistic limit in case of particles moving very fast. Today, we see another evidence of quantum mechanics, and that is related to the radiation from a black body. Black body means an object with a constant temperature emitting electromagnetic wave, and we treat this one to simplify the problem. We treat it to be a cavity that, that contains the empty space, and the temperature is well controlled to have a constant temperature, so that the equilibrium makes the radiation of analytically solvable system. People use the Maxwell's theory to resolve this problem, but unfortunately, we shall find that this theory breaks down in the limit where the wavelength becomes shorter or frequency becomes larger. So the black body radiation is parameterized in terms of spectral radiancy. Spectral radiancy. The black body radiates electromagnetic fields, and the amount of energy radiated by that black body can be parameterized by the radiation intensity. Intensity is the energy deposit per unit area per unit time. So energy per time is can be written as a power per power. So the intensity is a power per unit area. Because there are various wavelengths contribute to the total radiation, we define the spectral radiancy is a probability distribution of this energy density. So intensity per unit wavelength. If we draw a curve with respect to the wavelengths, there are two ways we have speed of light, the wavelength over period, so wavelength times frequency. These two variables are correlated, and we can make a change of variable with respect to nu instead of lambda. Then the shape of the distribution may change. The functional dependence appears in this way. So spectral radiancy can be integrated over the whole wavelength to have the normalization equal to the radiation intensity. Mm, After substituting this change of variable relation, we can rewrite this. There's a typo. We have to remove this one. So after substituting this relation into this integral, we can rewrite the integral over the wavelength in terms of the integral over the frequency. And this tilde is the radial spectral radiancy depending on the frequency. And the explicit form can be found in this form. We can substitute lambda to be c over nu, and that is substituted in here. and Jacobian C over nu squared appears here, the sign flips the order of the upper bound and lower bound of the integral, uh, upper limit and lower limit of the integral. So if we applied Maxwell's theory, we can find the electromagnetic field inside the cavity. Well, for simplicity, we consider the one-dimensional propagation along the z-axis. Kz minus omega t dependence states that this electromagnetic is trapped inside cavity, and we notice the sine functions, and we expect that they are making a standing wave. So if we make an approximation with a conducting surface, then we propagate along this direction that this electric field vanishes inside the conductor. So by making use of this boundary condition, we can find the electric field and magnetic field completely determined in this form. The overall vector is the amplitude that is perpendicular to these two directions. To consider the electric field, that there are two polarizations that is perpendicular to the k hat direction. So there is a I hat and j hat. We notice that the magnitude of the magnetic field is completely determined. We, we remember absolute value of the electric field in the vacuum. Absolute value of the electric field is speed of light multiplied by the magnitude of the magnetic field. And the direction of the magnetic field is determined as a to form a cyclic triad. So IJK. So if it is along electric field is along this I direction, then the magnetic field will be along the y-axis. And if the electric field is along the y-axis, then magnetic field will be along the minus x-axis. That's the reason why this amplitude along the x direction for the electric field, the y direction for magnetic field, they are identical to each other. And the y component of the electric field is the same as the minus or negative of the x value of the amplitude. So the magnitude of the amplitude is just the square root of this sum of squares. And the magnitude of the magnetic field is absolutely correlated with the magnitude of the electric field. One thing we need to consider is the polarization vector. There are two polarizations. And we remember Poynting vector represents the energy flow of the electromagnetic field. Poynting vector, and in here, this is the Poynting vector, and this is the average of the Poynting vector, average over the space and time. Because of this cross product gives sine squared, because electric field and magnetic fields are always in phase, as we learned when we studied Maxwell's theory. The average of sine squared, either over the space and over time, is just a simple gives a simple RMS value. The 1/2 is the square average of the sine squared, and here By definition, we have denominator is mu zero, and factor of c appears before because we have replaced we have in order to make use of the identity, we multiply the c to the magnetic field and divide c outside. Then the magnitude is em squared, the electric field amplitude squared, and direction of propagation k hat appears in here, and this average becomes 1/2. The final result is in this form, and we are familiar with this. This is the electromagnetic field energy. Due, this is 1/2 epsilon 0 em squared. This is for the sine square kx minus omega t. This is for the electric field, and there's another from the magnetic field, and they are equal, but because of a factor of 1/2 coming from the space-time average, we have additional 1/2 factor appears. And that is actually the electromagnetic current density, the energy current density. All right. So using this idea, we can compute the classical radiation in the cavity. And just like what I have told, one-dimensional case is generalized to three-dimensional case. So consider a cube, and electromagnetic field is trapped inside the cube, a conductor, perfect conductor. To simplify the calculation, so this these the three directions we always have the sine function, and there the wave number is determined by three integers. They are all positive integers. The sine is just sine of, for example, plus minus one. They do not contribute any different contribution. That is just over uh, over. They behave like the over phase. In here, we have is the polarization vector, depending on the wave number depends on the x direction, y direction, and z direction. So we have pulled out the time-dependent factor outside. We, we just to consider a simple case of a spatial dependence of standing wave is described in here. By the way, this is two rather tedious calculation to you, and at the end of the day, you will find that this is of no use at all. However, it is quite still useful because later we can just the mathematical computation of this kind of wave function part is quite useful to study the bound state problem of quantum mechanics. So even though you don't have to seriously follow every detail, just keep in mind the basic idea of the classical treatment of the black matter radiation. So this sign can be rewritten in a simple expansion of the exponential of a forward and backward wave that results in the standing wave in three directions. We substitute this into wave equation. This is the resultant wave equation coming from the Maxwell's equation we already obtained. In the vacuum, both the electric field and magnetic field satisfy the same kind of wave equation. And we arrive at the dispersion relation because the time dependence brings in the frequency, angular frequency omega in here. So omega square over c square minus wave number, wave vector square appears. And for the electromagnetic field satisfy the wave equation, this dispersion relation must be satisfied, where this capital N squared is just like a Euclidean vector has components a nx and y and z that are all determined in here in the expansion. So we make some trick to compute this when n is a very large, because there is no limit of n. We need to sum over everything and sum over the two polarization states of the photons. Not here in Maxwell's theory. There's no photon at all. The electromagnetic field. Um, that summation, complicated summation for large n limit, can be considered as it approaches a Riemann sum. That means we can replace it as an integral. And the summation is now replaced with the three-dimensional integral for nx, ny, and z. We just replace this sum of integers as integral over the real variable. And because there is a summation over the two polarization states that are always transposed, we multiply a factor of 2. At the end of the day, this one can be expressed in terms of frequency integral. That, in addition, we learned in the first semester with thermal physics, statistical physics, thermal physics. In general physics 1, we learned equipartition theorem. And for each oscillation, such as a harmonic oscillator of degree 1, there is an error is 1 half kx squared. Then in each oscillator, for each oscillator, we have this kind of kinetic energy that in equilibrium of in temperature capital T, we have thermal, we have average kinetic energy of a molecule. If there are many molecules in it, so average energy is, because we are considering the free particles, the kinetic energy is the total energy of the system. And because the summation becomes integral, and still the integral has the two factor of 2 coming from the polarization states, we have additional factor of 2. And for a single dimensional, we have 1 half kBt. So, including all of this, our spectral radiancy in terms of frequency integral is like that. In addition, because radiation is propagating for all of the direction, this is our observation, and the surface of the black body, there's just a tiny hole at the black body. It depends on the radiation power, depends intensity, depends on the angle of observation. So if you're just above the hole, then the intensity becomes large. Okay, such kind of complicated consideration is also included at the end. We end up with the spectral radiancy that is called the Rayleigh-Jean's law. Unfortunately, this is most important. This spectral radiancy, in terms of this is wavelength, classical theories, Rayleigh-Jean's law diverges for a very small lambda. Lambda goes to zero. That means nu goes to infinity. This is quite important. This is called ultraviolet catastrophe. So classical Maxwell's applications of Maxwell theory completely breaks down, and we need to find the correct theory. That's the one of the most important necessity of the quantum mechanics. This radiation pattern for large lambda is not divergent. So the spectral radiancy has the strict divergence in the limit lambda goes to zero, but the tail at large lambda seems to be okay. So this is the formula, not derived from the some fundamental assumption, but just to fit the data. For example, if lambda is very large, then this one can be expanded in Taylor series expansion, and we can find this one. This is just lambda kbt over hc, and we have denominator lambda to the fifth power, and one lambda cancels to reach lambda to the fourth in the denominator. Lambda to the fourth in the denominator is reproduced. Max Planck just found just introduced this kind of ad hoc solution to reproduce the larger lambda tail, but that is not divergent in the limit lambda goes to zero. And this function fits quite good in comparison with the experimental data. But actually nobody knew what the reason for this agreement. But finally, some computation based on the quantum analysis that single photon has the energy of E nu. We now know based on the photoelectric effect, and we have confirmed this based on the Compton's effect, Compton scattering. The total energy of n photons with the same frequency in the cavity is this. If there are n such photons in the cavity. Actually, this is a kind of harmonic oscillator, and the energy level of the electromagnetic field coming from the harmonic oscillator is h nu multiplied by integer. That's the solution. And the overall factor that contains the exponential one is actually, we can rewrite this factor e to the minus lambda over kT hc. 1 minus e to the lambda over hc kT. This is identical to this, and This is a kind of geometric series, infinite sum of the geometric series. Right? 1 minus r. It is related to that one. So Boltzmann distribution states the probability of having such kind of energy state. The photon has a specific frequency, but photons are emitted from the quantum harmonic oscillator in a cavity, and quantum harmonic oscillator has a discrete energy level that is multiples of h nu. Then, as a result, the energy of the total energy of the electromagnetic field is actually the total energy of the photons, and these photons must have the energy of n times h nu. So if we consider the probability of having one single photon, two photons, three photons, n photons, such kind of state has a probability weighting factor like this, and then all of the probabilities should be averaged over. So sum of those probabilities and EI is a proportional to the multiples of H nu. So as a result, this Planck's radiation law is completely understood in terms of quantum theory of a harmonic oscillator. All right, and then Einstein explained it, and that is just what we have just commented. And Boltzmann distribution is a probability of having such kind of state in the cavity. So in summary, apostrophe is missing. This is Einstein's explanation of Planck's law. First of all, the energies of atoms are quantized as nh nu. Nu and h nu is energy of a single photon, and nh nu is that photon's energy is multiple. So n runs from 1 to infinity. This is equivalent to n photons with frequency nu. Okay? So cavity, wall of the cavity, they're consisting of charged particles, and charged particles emit can photon, and their state is kind of harmonic oscillator. Simple assumption. In that case, actually, if we learn quantum mechanics, the energy level of the harmonic oscillator is a multiple of some fundamental frequency. So h nu multiplied by n, and that shift the atoms has energy levels with difference h nu, h nu, h nu. So the ground state between these transition will emit photon of h nu, and this transition will emit photon of 2h nu. Simply, if we simply consider the two states, then the energy difference is h nu, and it emits n such transitions, then it will result in the n photons with the same frequency. And the thermal equilibrium between the cavity and the electromagnetic field is replaced with the n photons, and they make some equilibrium state. But this derivation needs some your understanding of thermal and statistical theory. So let me do not go further and just summarize. If you learn physics more to that stage, then you will understand better. So anyway, the probability of having that kind of state of energy, NH nu, is exponential of energy divided by kBt. This is the Boltzmann distribution of thermal physics, and it is allowed to have a 0 to infinity number of photons. Then the state has the probability with the various probability and uh, probability density and absolute probability of a certain amount of energy, and h nu can be expressed as that proportional probability density divided by the sum of all of the probability density. So this denominator gives the geometric theory. So average energy is the sum of this probability multiplied by each energy, and we'll find that average should be this. If in order to have find out the average, you have to sum all of the energies weighted by its own probability that is determined by this Boltzmann distribution. So using this expression, we sum over n, and denominator numerator, they are both very similar except that we have a factor of n in the numerator. So it's because energy is a multiple of h nu, there's an n factor in the exponential hidden in here in en. So it is convenient to take the partial derivative with respect to x and put the negative sign on it. Then you can absorb that factor of n into in here. Then in the denominator, and before taking the partial derivative, the numerator becomes the same. And summation, therefore, this one can be expressed as uh, because it's something in the denominator and its derivative is above. That is just a log, derivative of log. So minus x derivative of log, right? And then the argument of log is the sum of these. This Some of this geometric series are trivial, and actually this is 1 over 1 minus e to the minus x, but we we take the reciprocal and pull out the negative sign to remove this negative sign. So we end up with this. And taking the derivative of this is trivial again, and final result is expressed in this. And because x is h nu over kBt, we can substitute this to find out the energy, average energy of the cavity photon system. Substituting this one in here, we finally obtain the spectral radiancy. Okay? This one is to replace the kBt in Rayleigh's law. In here, replacing that average energy with this one, we finally obtain the expression that Planck obtained. This Planck's radiation law was fit to an experimental data, and it was not explained clearly. Finally, Einstein solved this problem by considering the quantum effect. All right. So once this spectral radiance is determined, then we can derive further to find the place where the peak of the spectral radiance is placed. That that is Wien's displacement law, and we carry out integral to find out the total rate, and there, there is a simple derivation to find out that intensity is proportional to the absolute temperature horsepower, and over a factor is called the Stefan-Boltzmann constant. Okay, so this blackbody radiation problem that had ultraviolet catastrophe, if we only consider the Maxwell's theory, this problem was completely resolved by the first of all the fit to the experimental data, and then it was clearly understood by some simple assumption that the atom has energy level of h nu multiplied by integer, and thermal equilibrium with that atoms with photons explained this Planck's radiation law, and that is not divergent at all, and fit to the data as well. So we are ready to believe that we we might have to construct a theory to describe the wave nature of particle, because the quantized state of atom seems to have some bound state in a just like a vibrating string that has a certain frequency, except that the any other frequencies decays with an exponential rate, and resonant frequencies are just multiples of the fundamental frequencies, something like that. That that is quite this quantized behavior of the bound state is quite similar to, not exactly the same, but very much similar to the string vibration, the boundary value problem. So, having found the quantum nature of particles and quantum nature of photon, that is the quantum of the electromagnetic field, we would rather want to construct a theory based on the wave mechanics to describe the particle whose behavior can be completely understood in the non-relativistic limit, where the fundamental particles are all averaged over a very large number of particles or something like that. So we have two new concepts. First, quantum physics based on the wave mechanics is necessary. The second one is the special theory of relativity that must be included if you consider or want to consider the theory of photon, and especially the electromagnetic field should be interpreted as a photon when It interacts with fundamental particles like electron, proton, something like that. But the structure becomes a very large and averaged over then the classical limit. We reach the classical limit and not a big problem present. However, even in that case, a photon is moving with the speed of light, and that that is the key. So we want to construct a quantum theory based on wave mechanics. We already stated de Broglie's wavelength lambda equals h over p is based on the completely relativistic theory. In wave mechanics, unlike classical theory, it is impossible to fix both position and momentum simultaneously. Here, p is determined by wavelength, and wave is always expressed in terms of, for example, exponential kx minus omega t style. And frequency, it's better to write down this speed v, wavelengths multiplied by frequency. So wavelength is in here. Right. So momentum is h over lambda, and we may insert 2 pi in the denominator and numerator, keeping the same. And this is called the reduced Planck constant h bar, and this is a wave vector, wave number k. So this wave has a certain momentum because the k is fixed. However, the probability of finding this particle, this wave, can be interpreted as intensity at any point. In this case, exponential absolute value squared it can be interpreted as the intensity or interpreted as the probability density of finding a particle based on the fact that we used when we consider the interference pattern due to a Young's experiment, the brightness of the bands reflects the intensity of the light, that is actually the amplitude square of the electric field. So if we use, for example, this kind of monochromatic wave of a certain fixed wavelength, the momentum is completely fixed. However, the probability of finding this particle all over the space is absolutely flat. So momentum is fixed. However, the position of particle is distributed all, all over the space. So it is impossible to fix the coordinate and the conjugate momentum. Momentum in non-relativistic theory, momentum is mass times velocity. So position and momentum cannot be determined accurately simultaneously. That's the big difference between the wave mechanics and classical classical theory. In classical theory, equation of motion is F equals ma. That is, we know the force is minus gradient of potential energy, and ma is just time derivative of momentum. And this problem is completely solved, and you will know what the xt is if you can solve this problem. Even though it is rather complicated, you can find the numerical solution for this, and then you can obtain the velocity out of the answer for the displacement, and then multiply mass to find out the momentum. And they are both p and x can be determined simultaneously and in principle accurately. Next, if we consider the wave mechanics, we can consider the interference. Interference is based on the superposition principle, just like when we apply two forces, resultant force is computed can be computed as a vector sum. And if we consider a wave, two waves can be added as an algebraic sum. So linear combination of waves is another wave, so they can interfere. So this kind of interference can be uh, understood as a source of interference. The, the interference will result in the change in the distribution of probability of finding a particle in space, just like the case that the fringes on the screen out of the result of the Young's experiment may vary depending on the position. Next, what we would like to consider is using wave. We would like to describe some particle nature. Our most important relation that is conservative. So is the total mechanical energy if the potential exists. That means the force is conservative, then conservative force, then it is always expressible as a minus gradient of potential energy. And in that case, we have the Hamiltonian, the total mechanical energy is conserved. Total mechanical energy is the sum of the kinetic energy plus potential energy, something like that. What we would like to require is that this fundamental principle of classical mechanics must also hold in wave mechanics, keeping the energy invariant if the force is conservative. So we would like to find some wave equation that respects this fundamental conservation theory. First, let us try a very simple wave that is a monochromatic wave, e to the I kx minus omega t. This is a one-dimensional monochromatic wave, plane wave, moving along the x direction only. If I want to pull out the information of wavelength, it's very simple. This is exponential function. What I would get is taking the partial derivative with respect to x. Then wave function. What I get is ik. And we still have the same wave function. Exponential is good. But we have k, then with k I can construct the momentum because de Broglie wavelengths can be used. This should be h bar k, a vector. So in order to replace this one with h bar k, what I need to do is just multiply h bar over I, partial derivative, and wave function. If we use, or if we want to make use of wave mechanics, so we need a wave function. And we need to apply some mathematical operator that is usually the differential operator to read out the wavelength or frequency. Reading out the momentum is just to take the spatial derivative. This is just for the single dimensional, one-dimensional case. If you consider the three-dimensional case, this one can be generalized into the gradient. H bar over I gradient is applied to the plane wave. That is a vector. We use vector kx minus omega t, something like that. Then what I would get is h bar k vector. So momentum p is obtained if for a plane wave case. So with a very simple idea of using plane wave in three-dimensional case, if I want to read the momentum p from this plane wave, what I need to do is h bar over I gradient of this wave function. In a similar manner, I can read the energy. We begin with the theory of photon, E equals h nu, and that is h bar omega. Why don't we use this kind of formulation? Energy is the frequency of the wave up to over a factor that is a reduced Planck constant. Then what I need to do is, instead of taking the derivative with respect to spatial coordinate, I need to take the derivative with respect to time. And then there's an over negative sign in comparison with the spatial part. What I get is I put the I in the numerator and take the time derivative of the same function. Then I obtain energy. Alright? So, in this manner, I can construct some ad hoc equation based on the basic assumption that elementary particles behaves like a wave, and their wavelength is determined by the de Broglie wavelength, and de Broglie wavelength is completely relativistically defined one. h over lambda. And using this, we can pull out the information of momentum out of a plane wave solution. So this is the momentum. This is the operator that reads the momentum out of the plane wave solution. And this is the energy operator that is called the Hamiltonian to read the energy, total mechanical energy of the system. If it is can be expressed as a very simple wave that is a plane wave. All right. And then in a realistic case, we can also include the potential energy and we can include the kinetic energy. Kinetic energy can be simply obtained by p squared over 2m in the non-relativistic case. In that case, that is minus h bar squared, gradient squared, that is Laplacian, del squared. In a similar manner, the relativistic case, we can pull out the energy in this way. The energy is defined, the unshelled particle of rest mass m can be determined like that if there is no potential at all. Next step, in a plane wave case, we have I k dot x minus omega t. And this can always be factorized as a k dot x because it's exponential. If it is not factorized, it is very difficult to solve the problem. But why don't we first assume the wave function? Wave function is just like the electric field or magnetic field that is the function of the space-time coordinates. The spatial factor and the time-dependent factor are completely factorized. I don't know why, but just try. Just try, and if you can find a solution, that's it. We are not mathematicians. We are dealing with the actual problem in nature, and at first time we solve the problem, we probably don't know how to solve this problem, but we may try. But if there is a solution and a mathematician may help, that your solution is unique and there is no other solution you have not found yet, then that may be the general that becomes the general solution, and you can use that solution in any case. All right, and again, the probability of finding a particle is just the wave function squared, and actually this absolute value is not for a real valued function only. It is just in general the complex valued function. So free particle wave equation can be constructed in a straightforward manner. In just the previous page, we have discussed that the operator pulling out the momentum out of a plane wave solution is just h bar over I gradient. And if you assume in this case the time spatial part and time part are completely factorized, and if you assume the separation of this time dependence, this is called the variable separation if we learn partial differential equation. When they are separated, then this operator acts on the spatial part only, and the time dependent part is transparent to do this operator. Energy operator can be expressed as the partial time derivative, and then multiplied IH bar. The sign difference is due to the sign difference in here. All right. So, in summary, energy relation is just a simple wave equation. Schrödinger equation is a little bit more complicated. Energy is replaced with, in general, this energy Hamiltonian can be expressed in terms IH bar time derivative. And right hand side is a completely space dependent operator. This is the reason why our first trial, of factorizing the solution psi xt as a product of x function and t function. If the operator is just a sum of two operators, and the two operators are in the different space, one is time space, the other is completely decoupled, then such a factorization is allowed. Finally, energy conservation relation can be written in this form, and if we substitute the factorized form of psi t of x, t and x is factorized as psi, for example, psi of x and some t of t. This depends on the coordinate only, this depends on the time only. Then we can find the two equations. We can find that this reduced into two decoupled equations for only for x and only for t. The resultant equation that depends only on the x is called time-independent Schrödinger equation. Once you know the answer, then you can just multiply the frequency factor, that is e to the I omega t. And if the solution has some various energy that is called eigenenergy eigenvalue, then your solution will be psi of n, sum over n, with the coefficient constant, complex constant. And the psi of n is a solution of some energy, fixed energy. And you will find there are various possibilities of getting the solutions. So there, in general, there are multiple energy eigenvalues. When there are multiple energy eigenvalues, then the corresponding time factor should be written in separate form, and this is psi of t and x should be a sum over psi n x only, and then e to the minus h bar I e n t. And there's a cn, this complex number, complex constant. This is the final result for the solution of the Schrödinger equation. This time-independent Schrödinger equation can be in, for example, if it is just for one dimension, this is a second order x derivative, and we can reorganize this expression into this kind of form, and it's something like a simple harmonic oscillator, except that it is function of x. Okay, so if it is constant and there's some special value, we can find very simple solutions. But if it is a more complicated, the solution will not be solved in an easy way. Anyway, we shall consider only simple cases, fundamental cases that are very important for further studies. Anyway, as I have already stated, there is an uncertainty of coordinate at its corresponding conjugate momentum. Conjugate momentum is x conjugate momentum is p of x, y's conjugate momentum p of y, and z of conjugate momentum is z p of z. Both of them cannot be determined with an absolute accuracy simultaneously. That is true for this pair and this pair. But it's possible to determine these two simultaneously. That's not a problem. But as long as the coordinate and its own conjugate momentum is concerned, for example, angle and corresponding angular momentum, they are conjugate relation, then they cannot be determined with an absolute accuracy simultaneously because we are treating the particle as a wave. If it is a wave, if wave is monochromatic, we can determine the momentum absolute with very high accuracy. However, it is distributed all over the space as a flat distribution. Okay, that's it for today.